name is Aleksandar Velkoski. I'm a data scientist at the National Association of Realtors, and today I'm going to be talking about how you can use Elasticsearch and Python to create a search engine that will allow your data to be searched by members of your organization or potentially your customers. And I'll show a couple of screenshots of our Realtor search, which is our implementation of Elasticsearch and Python in practice. So why did we think about creating a search engine? So first and foremost, we have quite a bit of data at the association, not quite as much as our friends at Argonne, but we do have enough information, enough data that makes it difficult for us to kind of go in and query and understand information about our members. Our data resides in multiple different databases. Some are in Oracle, some are in SQL Server, some are in MySQL, some are in Postgres. Some of our data that's actually very relevant to us reside in CSV files on individuals' laptops, which makes it actually very complicated for us to leverage that data and make it useful for our organization. So one of the things that we wanted to do is build a platform that took data from all these different places and kind of integrated it into one place. More importantly, what we really wanted to do is get data, important data, into the hands of non-technical business users as well as executives that make decisions about the association and about our business and strategize our business sort of going forward. So we wanted to create a platform that would make it very easy for people to query information without the complexity of actually writing queries. Why Elasticsearch? So obviously Elasticsearch is a document-oriented search engine, so it sort of fit very well with what we were looking for. One of the greatest things about Elasticsearch is that it provides some great functionality for unstructured search as well as structured search. So unstructured search is essentially full-text search that is tokenized and then basically goes through your data and it tries to determine what documents match the tokens that you put into a search and then returns results based on a score. Structured search is a lot more like a SQL query with a where clause, where you're actually trying to identify specific types of information from your data. So if you're thinking about trying to pull down sales between 2010 and 2015, that would be something more of a structured search. Elasticsearch is distributed, so it is scalable, and we appreciate that. It is API-centric, meaning that almost everything you would want to do in Elasticsearch can be done through APIs, so that's very powerful. And lastly, it is near real-time, meaning once you index a document, that document is available to be searched almost immediately. So it fit very well with sort of our requirements, what we were looking for to create a search engine. Some core concepts with Elasticsearch, an index, which is a named collection of documents that have somewhat similar characteristics. It is not equivalent to a database, but you can think of it roughly like a database. A type, which is a logical partition of an index that contains documents with common fields. So a type is, again, not exactly a table, but you can think of it as a table of information. A document, which is a basic unit of information. If you've worked in MongoDB, you kind of have a sense of what a document is. And then mapping, which is basically field properties, such as your data type, whether or not you'd like the field to be searchable, and how the query should actually tokenize the field when a search takes place. So let's take a look at an Elasticsearch document. So Elasticsearch documents are modeled as JSON objects. So as I mentioned on the previous slide, if you have any experience with MongoDB or with JavaScript or with dictionaries in Python, you'd be very familiar with a document in Elasticsearch. As you can see, a lot of the core data types that you would be working with are supported in Elasticsearch. So you have strings, but you also have more complicated data, so arrays, objects, and things that I really like geopoints and IP addresses that allow you to do some more advanced searching based on location, based on IP ranges, and things like that. So Elasticsearch provides a very great method for you to go ahead and do some searching on data that is relevant to you and your organization. Creating an index is very, very easy in Elasticsearch. All you have to do is send out an HTTP exput request to localhost 9200. This is the standard location where Elasticsearch is going to operate if you do not provide it with other configurations. So in this case, after you say localhost 9200, you're going to pass the index name. So in this case, the index name, we define it as MMPS. And then if you would like to provide Elasticsearch with some settings for that index, as well as mappings for various fields, you can do that. If you don't, then Elasticsearch's standard defaults will be provided. Elasticsearch will assume things about your fields if you do not provide it with information about your field. So if it can infer that a field is an integer, then it will go ahead and call it an integer. Otherwise, it will typically fall back as a string so that it is searchable. To create a document, it's very similar syntax as you saw on the previous slide for creating an index. The only thing you have to add is a type, which in this case we define as a member type, and then an ID. Once you do that, you pass the actual document that you're interested in indexing. In this case, a first name, a last name, and some membership information, so whether or not the status of this member is active, and the type of membership that this member has. And then this will provide you with the ability to index that document in Elasticsearch. So once you create this request, the document will be added. If you create this request in Elasticsearch but not create the document or the index first, then the index will automatically be created for you. So if this is the first document that you're indexing, you theoretically do not have to create the index first, but this is, again, a great option for you when you are inserting documents to an index. There is a Get API. The Get API allows you to request a very specific document from your index. So in this case, the Get syntax is very simple. Localhost 9200, you tell the request what index you are interested in searching, what type you're interested in searching, and the ID of that document, and then you will receive a response which tells you what index and type you searched in, what the ID of the document is, whether or not a document is found, and then the source for that document. So when you are, I'll show you how to do this in Python, but when you're in Python, this is fantastic because everything is given back to you in basically dictionary. So you can go ahead and manipulate it and do things that you need to do within Python. It's actually quite powerful. The search API is where Elasticsearch actually now differentiates itself. So with the search API, you can actually find documents based on free text search. So instead of searching for a document based on a very specific ID, you can sort of give it free text parameters, and Elasticsearch will provide you with documents that best fit those parameters. So the first one is basically search light. So if you just want to do a very quick search with some terms, you can go ahead and add the search variable at the end and then add whatever term you're interested in searching or phrase, and then Elasticsearch will provide you with a response of documents that best match that search. Or you can use the more complex query DSL, which allows you to leverage some more advanced querying technologies rather than the search light, which basically provides you with just a match-all query. So I'll talk a little bit about your query options in a moment. Searching, so this is the response that you receive when you do a search in Elasticsearch, whether it's search light or through the query DSL. So along with information related to the amount of time it took to return the documents and the number of shards that were used, you'll be provided with the number of hits. So in this case, the total hit for a search for Alexander returned 1 document. The score associated with that document, so when Elasticsearch goes in and determines what documents are relevant, it considers term frequency in a document. It considers inverse document frequency. It considers any boosting factors that you provide to Elasticsearch, saying, hey, certain terms are very important to me, so I'd like you to boost that in the search, as well as a couple of other things to optimize that score. Once you sort of get an Elasticsearch and get it up and running and learn how to use it, you can actually customize that score based on things that are very important to you. So instead of Elasticsearch assuming what documents are relevant, although it does that very well, you can customize that in whichever way you feel is most appropriate. Here are some of the high-level types of searches you can do with the query DSL. There are many, many more than this. I encourage you to look at elastic.co to figure out all of the different options for search. But there are terms queries, which basically search for an exact match for a term. If an exact match is not found, then no document is returned. Whereas in the previous search, the match-all query, documents were returned based on documents that may match that term. Multi-match, which looks at basically a variety of fields that you suggest Elasticsearch to search in, instead of taking a look at a match all query where you're looking at all fields. You can say, I just want you to look in a few different fields that are important. Bool queries, so must match, should match, or must not match. They're sort of intuitive, but I recommend that you sort of take a look at what those actually mean. Common terms, so match more important terms first and then consider certain stop words that may exist in a query. More like this queries, range queries, you can use regex, and you can even do queries based on geolocation and IP addresses. So very, very, very powerful search capabilities that Elasticsearch provides. Now, for the Python client, Elasticsearch Pi is really the best Python client available for Elasticsearch. There is another that I've used just a little bit, but it's not as powerful. If you would like to install it, it's pip install Elasticsearch, very simple. In terms of the actual syntax in Python, you'll find that a lot of the syntax is going to be very similar to the HTTP requests that I showed on a couple of slides prior. First, you import Elasticsearch, then you call the Elasticsearch function. If you do not pass an argument string within the Elasticsearch function, Elasticsearch will assume you're operating on localhost port 9200. So if you configure Elasticsearch to operate on a different port, or if you'd like to connect to an Elasticsearch instance on a remote machine, then you would simply pass a string there with the IP address in the port, and Elasticsearch will connect to that instance. So then in this case, I have a doc here that I've written in Python. This doc is exactly like what you saw previous slide earlier, first name, last name, and membership status. And to create the index and insert the document into the index, all you have to do is call the index function in Elasticsearch. You pass the index argument, which in this case is MMPS. You pass the doc type, which in this case we've defined as member. You pass the ID, and then you pass the body of the request, which is in this case the document, and the document will be automatically indexed into the MMPS index in Elasticsearch. The response object will provide you with information about whether or not that document was actually created in Elasticsearch. So if you just call your response object created, then you'll kind of get a sense of whether or not what you wanted to happen actually happened. You can also search in Elasticsearch via the search option there. So again, you define your index MMPS, your doc type member. You go ahead and pass the body of your query. Your body can be a dictionary, just like we showed here with the doc, or you can simply write it there in line. So in this case, we're going to conduct a match query against all fields for the first name Alexander, and then you will receive a response. If you recall in the previous slide, the response has the total number of hits that was associated with that search, as well as the source document for any documents that were actually returned. So if you received many, many documents, you can iterate through those documents via a for loop to actually go through and see what documents were returned. To actually implement this in an application with a graphical user interface, we have chosen to use Web2Py. For all of the reasons that have already been outlined here today. But to do this, it's actually very, very simple. So in your index page, you create a form. The form can either be an HTML form, or it can use the helpers that Web2Py has available to you. You have an input, a text input in this case, and that's pretty much it on the index page, unless you want to have any other very interesting things in your GUI. Then in the controller, you call Elasticsearch in the same way that we did on the prior slide. You define your page, and then when you receive your query, what you're going to do is you're going to pass the parameters to Elasticsearch, and you're going to have a response, and then you can return those local variables to whatever page that you would like to. So now I'd like to show you this actually implemented in a Realtor search that we created at the association. So we wanted this to be a lot like a Google search. So we wanted non-business users, or non-technical users to be able to write queries and receive information that will be relevant. So you see here, someone can go ahead and they can type in a name. They can search for the name, and the response, in this case, we only have one document. It's Alexander. So I was found. You can click on the person's ID, and you receive basically a profile of the person that provides you with a bunch of information about their level of engagement with the association and your level of engagement with them. So if you think about, for example, a call center, where people are calling in and they're asking questions, they have comments, maybe they're upset about something, many times people in your call center may not have a good sense of who they're actually talking to. With a system like this, when somebody calls in and they're provided with a name or an ID or some other information about themselves, the person in the call center can actually conduct a search, find the person that they're looking for, and immediately understand whether or not this person is engaged with you, how important they are, do they hold any positions, do they hold any committees, have they attended any meetings, have they donated to our political action committee, have they subscribed to any marketing newsletters? So if they're interested in some information and maybe they're not sure where to look, well, that would be an interesting place to take a look and see whether or not they've subscribed to some of those communications. And then last but not least, any contact information that may exist for state and local associations. In my case, I don't have any because I am staff. But all of this information is now readily available to anyone that's interested in searching. There is also a percolator that Elasticsearch provides, which is very, very interesting because it's essentially search in reverse. So you can be notified when certain people, in this case, certain members match certain criteria that you're interested in. So if someone is appointed to a committee, I may want to receive a notification about who that person is, what committee they're on, and I may want to follow them. I may want to learn more about them. So there's some really cool things you can do with Elasticsearch in Python, and this is just one implementation of how we've been using it. Does anybody have any questions? Yes.
So did you consider any other search engines like Apache Solr, and if so, why? What made you choose Elasticsearch?
Yeah, it's a very good question. So Elasticsearch Solr is a very good platform, and I think the one thing that we really liked about Elasticsearch is one, it has significant support out there in the community. So if there were any issues that we needed to deal with, we can count on people to be there and to support us. I know Solr has similar things. But the percolator was a big deal to us, and that is something that's in Elasticsearch but not available in Solr. So as I mentioned, the percolator is search in reverse, where you can create a saved search that will essentially notify you when an individual meets certain criteria, in this case a member, to basically, then you can follow them, you can do other things that you may want to do with those results. I don't know if Solr has a percolator, but that was very important to us. Yes?
As a user of Realtors, what I would love to have is some search that tells me, for this geographical zone, this Realtor has sold in this price range, and these, there is a seller and a buyer Realtor, so there is a graph of Realtors. And so I want to know the centrality of Realtors, so that, if they know each other better, they may know, better what's going on. Right. So if you gave me something like this, it would be great. Is any chance we can see anything like this coming out?
I can take that back and have conversations with the right people about that, but I think things like that are in the works, and with tools like Elasticsearch, things like that can actually take place very quickly. Yes?
What's the performance like, especially as data scales for the non-indexed, like the more generic searches you were talking about, and then how much of that requires the stuff sitting in RAM versus not?
Yeah, so that's a very good question. So the question was in terms of scalability of search itself or of indexing documents?
Of search and the non-index searches. You were talking about the generic searches you can do and how it has the scores and all that, right?
Well, all searches are basically index searches. So every document that you index in Elasticsearch is indexed, and every field is indexed. Some fields are not searchable, but at that point it will not be part of the search. So does that make sense?
Okay. And how does that work then with memory requirements and things? Does all this stuff have to sit in memory, or is it performant enough that you don't need a box with enough memory to hold all your data?
No, definitely it's not a memory issue. So Elasticsearch is distributed, so there are shards, and when you have an index of, let's say, millions of records, not every single record sits in the same place. There are partitions where various records exist, and when a query is conducted, Elasticsearch will do some optimizations to determine where that record is actually located, and then it will return it based on where it sits in the shard. Yes?
You mentioned you've had structured and unstructured data. How does Elasticsearch help you in indexing across structured and unstructured and unifying the query experience?
Yeah, so the question was about structured and unstructured data. So when I made the comment earlier about structured and unstructured, I was talking about search. So free text search versus filtered type of search, where you have a very specific parameter that you're interested in returning. But in terms of structured and unstructured data, Elasticsearch handles it very well. So if you have date times and you map that data as date times, you can conduct searches against that data in a full text search environment, because Elasticsearch has one field that is a string that takes all of the data that you've indexed and then makes it searchable that way. Or you can search for it via a date time as a field itself. So that's really the beauty of Elasticsearch, is it allows you to use structured and unstructured data when you're developing it and storing it.
Okay.
Any other questions?
Thank the speaker again. I think we have to move on to the.
Okay.
I think we have to
Thank
move
you.
on